Remember Kepler's law? This t squared equals 4 pi squared r cubed over gm. This super annoying equation because time, the period here, time is in seconds, and mass is in kilograms, and radius is in meters, and space meters are giant because space is huge. I'm going to show you how to get this equation into something way more friendly. But to do so, we're going to have to use some units that astronomers love to use, known as solar Earth units. Now, what I mean by a solar Earth unit is, let's consider the sun's mass real quick. The sun's mass is about 2 times 10 to the 30 kilograms. Well, how many suns then is 2 times 10 to the 30 kilograms? Well, if we just said the sun has a mass of this, then that is equal to 1 solar mass. Duh. Like, one sun is this amount by definition. That's what our sun is. That's how much mass it has. Okay, whatever. Now, let's also take a look at this value. If we assume this is our sun here, and this is Earth, the orbital distance from the Earth to the sun, or the sun to the Earth, depending on how you want to think about it, this right here, this is about 1.5 times 10 to the 11th meters. Okay, it's about that. This is what is known as an astronomical unit, an AU. It is the distance from the Earth to the sun. So by definition, we call this 1 AU. Now, we know here on Earth that we orbit the sun. We go around it. Well, how long does it take you to go around the sun? Well, here, let's do this. Let's start at January 1st, like at midnight, right? So like the start of the day. And then let's count how long it takes until, like, I don't know, December 31st at 11:59. That's a year. Duh. So what we have here are solar masses, masses of the sun, AUs, Earth-Sun distances, and our period is in years. Okay? Now, if we think about this and we go and look at this equation here, this 4 pi squared over g, these are only there as constants. They are there simply because, based on the fact that we're using kilograms, seconds, and what was our other one? Meters, we're stuck with these constants that kind of pop up. But if we use clever units like solar masses, astronomical units, and years, this becomes very easy. Let's take Earth, for instance. Well, what's the period of the Earth going around the sun? The Earth's period is 1 year. Let's square it. Let's ignore these constants. We'll see why. Well, how far away is the Earth from the sun? What's its orbital radius in astronomical units? Well, by definition, the Earth is exactly 1 astronomical unit away from the sun, cubed. Divided by, what's the mass of the system here? Well, it's pretty much just the sun, because if we added the Earth to it, it's very negligible. So what's the mass in terms of suns? Well, it's just 1 solar mass. 1 squared is 1. 1 cubed is 1. 1 divided by 1 is 1. 1 equals 1. We've just proven this for the Earth. So if we use these special units here, solar masses, AUs, in years, we can just rewrite this equation as just saying period squared equals the orbital radius cubed, or the semi-major axis cubed if you have an ellipse, divided by solar mass amount. And that is way easier. I no longer have to remember g. I don't have to remember the 4. I keep forgetting pi squared, so I don't need it. This also does some nice stuff for us, because if we are in our own solar system, you don't even need this mass, because it's always just the mass of the sun. If you're in some other solar system where it's got a larger star, then yeah, you need to put something else in there. But for our own solar system, you don't even have to remember that, which is nice. What this does is it allows us to quickly determine orbital periods of things if you just know how far away they are. Or if you know how far away they are, you now know the period. So if we kind of think about this, you know, based on our little friend sheet, that the orbital radius of Jupiter, we're going to call this radius Jupiter, is equal to 7.15 times 10 to the 7th meters. Oh no, that's just the radius of Jupiter. I want the orbital radius of Jupiter. It's not that number. Where is it? From the sun, 7.78 times 10 to the 11th. There it is. 7.78 times 10 to the 11th meters. If you want this in AUs, well, just divide it by what an astronomical unit is. 1.5 times 10 to the 11th meters. This will put it in AUs. And because these are both times 10 to the 11th, if you've been following the back of the envelope stuff, we can just kind of get rid of those. And we can actually just say 7.78 divided by 1.5. And Jupiter is about 5.18 astronomical units away from the sun. Well, with just that, we're pretty much done here. I can now just say that t squared equals r cubed. And in our case here, I can just say that the period of Jupiter squared equals 5.18 cubed. If I want to get rid of the squared, I need to take the square root on each side. Remember, taking a root is like taking something to a fractional power. So I can take this to the 3rd over 2 power, or the 1/2 power, and find the period. That's a quick way of doing that. And this means that if we wanted the period here, we can just say the period is equal to 5.18 to the 3/2, or the 1/2 power, and 5.18 to the 1.5 power is 11.81 years. So it will take Jupiter 11.81 years to go around the sun. And this is a very nice thing for us, because I know how long a year is, and I know how long 11 years are. You know, like 11 years ago I was doing this. But if I said, oh, it's like 650 billion seconds, how long is that? Like, I don't count the seconds like that. That doesn't really make intuitive sense to me. So this is a slightly nicer unit for thinking about times, because these times can be very long, and years are a nice way to think about long times periods for humans. It's something we can relate to. And astronomical units are also very nice for us, because we know how far away the Earth is from the sun. Now we're just doing multiples of that distance. So Jupiter's like 5 times as far away than the Earth is from the sun, which means we're about 4 AUs away from Jupiter. So they're kind of nicer units to kind of think about quantities rather than like what is a billion meters. And that's why we kind of use them. But it's a nicer way to approach Kepler's law if you have these type of units, or if you convert to them. And it makes everything a little bit nicer. So it's a cool little secret that astronomers kind of hide to themselves. You need to remember, though, that when we use this, you've got to wipe out the 4 pi squared and the g. We've gotten rid of them with our equational setup, and we've just done this instead. Okay? So with that, this little video is finished. I hope that was helpful for you if you're having problems with Kepler's law to kind of way around things. So with that, adieu, take it easy, and have a good one.